Okay, so in this chapter we're talking about exponential functions. In other chapters, we've talked about linear functions, like y equals 4x is a linear function. We've talked about quadratic functions, like y equals x squared. We've talked about square root functions, y equals square root of x. So in this chapter, we're talking about a function like this, where the exponent is a variable. So that's the main difference of the functions we're talking about in this chapter. So exponential function. An exponential function is a function that has a variable exponent. Variable exponent. And the b is known as the base, and the a value is the initial value. Initial means starting value, or initial value. So to graph one of these, you just use a table of values, make an XY table, and you pick a couple x values. We could pick -2, -1, 0, and 1 and 2. And you're going to plug 2 in to the 2 to the x. So I'm going to work backwards. You have 2 to the 2, which is 4. That would be this point right here. And then you have 2 to the first, which is 2, which is 1 comma 2, right there. 0, 2 to the 0, if I were asking questions in class, it would be a 1. I'm not sure how I'll figure that out since I'm recording. But it would be a 1. That's the that's the 0 exponent property. You get a 1. So 0 comma 1. And when you put -1 in, you'd have 2 to the -1, which the negative makes it a reciprocal. So you have 1 over 2. So it's -1 comma 1 over 2. And you put -2 in, to the -2. That makes the base of 2 a reciprocal, and you square the base. So that would be 1/4. So it's -2 and a fourth. So here's what the graph looks like. Kind of has a curve like that. And that's called the exponential growth equation. And we could state the domain and range. The domain are x values that have a point on the graph. So the x values would be everything. Every x value has a point on the graph. So that would be -infinity to +infinity. So everything. Or you could also say all real numbers. And the range is not all real numbers. The range would be from 0 and above 0. So it would be 0 to infinity. And this 0 actually has a parenthesis and not a bracket. It doesn't have a bracket because you never touch 0. So if you think about it, if I draw another page up here, if you had 2 to the x equals 0, what number could you actually plug in for x to get 0? Well, if you try 0, it doesn't actually work because that's 1. Even if you try a really small negative number, that still doesn't give you 0. That does not equal 0. That equals a fraction, 1 over 2 to the 100. So you can never actually get an x value to touch 0, to equal 0. So that's why in the notes, this right here is a parenthesis, not a bracket. So next we'll do the end behavior. Right here it says to do the end behavior. So end behavior we did a while ago. It's x approaches blank as f of x approaches blank, x approaches blank, f of x approaches blank. Okay, so as x goes to infinity, so that would be over here, if you look at the function's going uphill. The function's going up. So you would say as f approaches infinity, the function approaches infinity. The other way, though, if you look at this way, as x's go to -infinity, the function doesn't go up, and the function doesn't go down either. The function actually gets closer and closer and closer and closer to one number, which is 0. So you'd say as f approaches negative infinity, the function approaches 0. We've never seen one like that before. We've always had infinity or negative infinity, but now we can actually get it approaches a number, 0. So we have another example. Let me erase some of this first. So we can make a table. We're going to graph this function. Make an xy table. You don't have to put 5 numbers. You can just put 3 numbers. When you put 1 in, for instance, we'd have 4 times a half to the 1. And 4 times a half is 2. So you have 1 comma 2. And when you put 0 in, you'd have 4.
1.
4 times a half to the 0. So it'd be 4 times 1 is 4. 0, 4. And then you have 4 times a half to the negative 1, which that would be 4 times 2 to the 1, because you take a reciprocal of 1/2. So that would be 8. So you'd have negative 1 comma 8. So here's what the graph looks like. And that's an exponential decay graph. And see if you could state the domain, range, and the end behavior. So the domain would be all reals. The range would be 0 to infinity. Again, with the parenthesis at 0, since you never touch 0, it's an asymptote. You approach 0, but you don't touch 0. And the end behavior, as x goes to infinity, that's this way, the function doesn't go up and the function doesn't go down. It's gradually getting closer and closer and closer and closer to 0. And as x goes to negative infinity, the function, let's see, negative infinity is this way. The function goes up to positive infinity. So that's the end behavior. And the next box mainly summarizes the graphs that I just graphed so you can read the box. I've given you the next one to see if you can graph yourself, so you can pause this video and see if you can make a table of values, state the domain, range, and end behavior. And the answer is going to be appearing on the screen very soon. If you need to, when you're putting numbers into the function, like negative 1, into the x, you could use your calculator. It would look like this. 5 times 2, 2 raised to negative 1. And you get 5 over 2, which is also 2.5. So 5 over 2, or 2.5. And then you can continue. Here's the answer. Pause this video. On the next page, we have 2 types of exponential functions. So 2 types written in this form, a, b to the x. If the b is greater than 1, it's called exponential growth. If the b is between 0 and 1, it's exponential decay. So if you had a function 3 to the x, the 3 is greater than 1, so it's growth. And if you had 1/4 to the x, the b is between 0 and 1, so that would be exponential decay. So determine whether the function is exponential growth or decay. The first one, since you have a 4, is your base. 4 is greater than 1, so you'd say it's exponential growth. The next one, your base is 5 over 2. 5 over 2 is 2.5, and that's greater than 1. So you'd say that's exponential growth. The next one, 0.75. 0.75 is between 0 and 1. So you'd say that's exponential decay. So decay is the opposite of growth. If a plant grows, it's alive. If a plant decays, it's dying. Decay. The next one's a little tricky. Be careful about the negative exponent in there. So this is y equals 0.2, 1/5 to the x, to get rid of the negative exponent. So 1/5 is between 0 and 1. So that would be exponential decay. Some examples of exponential growth and decay that we'll talk about in this chapter. Population growth. Population can often be modeled with exponential growth formula, population growth. Also savings accounts, money, savings accounts, is often exponential growth. So you get a percent, like 2%. So for instance, for savings accounts, if you had 2% interest and you put $100 into account, after 1 year, you would have your $100 plus you just made $2. The second year, you would get 2% of $102. And the next year, you're going to get more. So every year, you get more interest because you have more money that you're making a percentage on. So it's exponential growth. So basically, the formula would be 100 is your initial value, 1.02 is how much you're making with interest, raised to how many years you have the money in your account. So it would be exponential growth. So it would look like this, and it would go uphill. So that's an example of exponential growth that we'll talk about next week. We'll do a lot with finances. An example that I like to share for exponential decay is called March, this month. This month is March. March Madness. And I'll write it really big for you so you can see. Let me just scroll down. March Madness. March Madness. March Madness is a college basketball tournament in the United States. And you start with 64 teams, and you basically have a bracket where Team A and Team B will play each other, and whoever wins moves on to the next round. So, Team A wins. The next round you might have C and D might win. And then you have 64 teams. So, A through Z plus a lot more teams. So this might be E versus F, and then, E wins. And D wins here. Whoops. Z and Y. Z, there we go. So then Z and A play, and A wins, and then A and D play. So it's a bracket, is what that's called. So March Madness is an example of exponential decay. So you start with 64 teams. And those teams match up head-to-head, and whoever wins moves on, whoever loses goes home. So after one round, you have 32 teams. And then they match up head-to-head, and then you have 16 teams. You have 8, 4, 2, and then 1 is the champion. And this is actually starting, well, according to this video, which I recorded on March 4th, 2013, this is starting in about 2 weeks. So it's about March 18th, I think, is when they start playing games. But this is exponential decay. You start with 64 teams, and you're losing half of your teams. So that would be 1/2 is your base, and X would be the round. So after the first round, you have 32 teams. After the second round, you have 16 teams. And there's 1, 2, 3, 4, 5, 6 rounds until the champion. So that's an example of exponential decay. And we'll talk about other examples later in the class notes. Okay, the next part, the last part of the notes, we'll solve some equations. If you'd like to continue with these class notes, you will find it on part 2 of this video.